Yeah, so Antoine asked me more or less kind of to spend half of my talk to introduce the diagrammatic Monte Carlo technique because it will be used later in some of the other talks. So maybe spend a little bit of time trying to introduce the technique and where we stand. Some of the news probably are not yet implemented at the software level, so this is probably our future. If I have time at the very end, I'll show you a couple of results for the interactive topology in independent model. So that's the plan of my talk. So first I will just do a small introduction. At the very end of this introduction, I'll say, okay, well, we have some new ideas how we can essentially make sure that all diagrammatic extensions always converge. So this will be the notion of homotopy action, and I will explain how potentially you can use it. And then if I have time, I'll just show you how the technology of diagrammatic Monte Carlo was applied to get the phase diagram of the Hubbard model. So let me start by simply making a very simple statement. So if we have some regular Hamiltonian for interacting fermions, no restrictions on the dispersion relations or the density, and some generic two-body forces, you can add three-body forces as well if you want, so they're kind of more rare. So I'm saying just, okay, well, the Hamiltonian or the interacting electrons themselves, they don't have a sign problem. So the sign problem comes only as a method which is used to compute their properties, because the system itself is perfect. Add the voltmeter and you know the answer. So probably I have to make one excuse, which is very important. So this Hamiltonian has to be regular. I have nothing to say about the Hamiltonian where, say, all parameters in this Hamiltonian are, say, random with a limited range of support, because you immediately understand that if I write down this Hamiltonian and allow all parameters to be random, that's the entire material table, and any possible material with any possible phase is part of it. If you want to do an honest job on this Hamiltonian, essentially, yes, you simulate the whole universe. There is no ambition to do it. So you have to more or less concentrate on a regular system one by one. And then I say, yes, we can solve it. So it has to be a regular system. I'm not talking about disordered ones. So let me kind of first introduce one simple notion, which more or less everybody is using. Basically, that's computational complexity. I'm assuming that in a thermodynamic limit, the exact answer is not direct. So the problem is not solved. So essentially, then we have to ask the question, okay, if you're interested in some quantity Q, name your accuracy, how well you want to know your answer in thermodynamic limit, and then try to see, okay, how the computation time will scale if you want high and high accuracy. So the computational complexity problem is solved if you can improve accuracy in polynomial time. If you claim better accuracy, but your time will scale exponentially in 1 over epsilon, yes, we have a problem. Essentially, we hit the wall and it's impossible to improve it. So polynomial scaling, for me, constitutes the solution of the computational complexity. And I will try to argue that diagrammatic Monte Carlo for interacting fermions solves the computational complexity. You can improve error bars in polynomial. So that's the message. Probably I will not spend too much on saying that, well, we have to talk here about the thermodynamic limit because academically speaking, sooner or later, any method will be subject to central limit theory. Whether you can reach this limit in practice, that's a separate issue. Sorry.
Carry on.
Yeah.
I'm sorry. Oh, sorry. Oh, excuse me. Yes, sorry.
The problem is that you were not apparently not broadcasted.
That's probably some problem, but I will not repeat it.
Yeah, no, just carry on.
You may want to pause for a couple of minutes.
Okay, so essentially I formulated the computational complexity problem. So we want polynomial scaling with inverse accuracy bound. Now, what diagrammatic Monte Carlo is doing? Essentially, diagrammatic Monte Carlo is saying that I am going to compute this answer, not for a particular sample with given degrees of freedom, including all the particles. Instead, you completely rewrite the problem as mathematical formulation. And you start doing connected Feynman diagrams, which you can write down directly in the thermodynamic limit. So just because it's already a thermodynamic limit, I don't have to worry about finite size corrections or finite particle number. So in this sense, the sign problem as we know it is completely absent because there's no scaling with particle number. It's immediately thermodynamic limit. Well, but what you do then, if you represent your quantity of interest as a series, when you just do expansion Feynman diagrams to high order, you write down your answer as power series and some parameter. Sometimes this is a coupling constant, but I'll show you the nature of the expansion parameter. So that's what we're trying to do. And then the entire computational complexity essentially goes into computing those coefficients. So realistically, yes, you can do maybe up to 10, sometimes even 12 terms in this type of power series. But the coefficients themselves are sometimes very expensive because you have to do the integration of all the internal variables which you have in your graph, plus you have to sum through all the topologies. Unfortunately, some of the symbols are not working on my screen, so I convert it to something else, but it's readable anyway. So that's the symbol for all connected topologies. Maybe you change the nature of the projection line. You have to do this in a complicated solution. The current algorithms more or less say that going through all the topologies is probably doable by brute force. So essentially all algorithms currently which are efficient, they sum through all the topologies explicitly. So you do Monte Carlo only in the space of internal variables. But you have to do it. But once this job is finished, you have power series for the quantity of interest. Okay, so just let me emphasize again. There are no particle numbers here whatsoever. So that's why the conventional sign problem does not apply. But you have a couple of sign blessings, which is happening in the diagrammatic space. One of them is that the only way how this type of expansion can converge is to consider fermions. Because for fermions, you have a generic argument that if you have proper regularization of the ultraviolet at finite temperature, the series have finite convergence radius. Finite convergence radius, despite factorial complexity in the number of diagrams, is only possible if diagrams cancel each other. So the entire premise of doing this type of calculation to have convergent power series, but for power series of this type to be convergent using finite diagrams, they have to cancel. So you need sign to make everything work. So it's actually not your problem, that's your blessing, because the only way how you can get convergent series is through the cancellation of them. And this will happen generically for lattice type models. And the second one, that the most efficient algorithms, which you have to perform the job, they are based on determinants. These properly manipulated determinants, but determinants are coming from the fermionic cycle. So that's our sign blessing too. Fast algorithms because of the sign, cancellation of diagrams because of the sign. So it's not hurting you, it's helping. Now let me explain why the entire setup solves the computational complexity problem, because I will approximate my quantity of interest by simply considering some truncation in my power series. And so if the series converge, then you can easily estimate what is the arrow bound. So the arrow bound is limited by the ratio of G over the convergence radius to some power n. So you immediately see that, okay, your accuracy bound increases exponentially with the diagram. So once I give you some accuracy, you can immediately estimate that I have to go to sufficiently large n, but I don't have to go any further. Now with fast algorithms, well, Ricardo Rossi was kind of at the beginning of this revolution. So the computation time scales only exponentially with the diagram model. And then you immediately see that you gain accuracy exponentially, but the time to get this accuracy is also exponential. So exponent versus exponent is the power law. So the only premise how all of this is working requires that the series converge. Well, that's the proof of principle, which was also done by Ricardo. You take Hubbard model, more or less generic parameters, but not too strongly interacting for the sake of demonstration. So you go U over T equals 2, not too weak, but definitely not strong. Temperature, beta equals 8, dose. So any other method would suffer from the same problem, conventional method. Simulating prime degrees of freedom in a finite volume. This is thermodynamic limit, and you already see that, well, free energy density is computed with accuracy of roughly 6 digits. Even if you have bosonic codes, it's very hard to get your answer with 6 digits. You know? But this is a fermionic system generically somewhere in the space of parameters. You can, this type of answers can be produced with accuracy of 6 digits. If your series converge. Okay, so that's the proof of principle. So if you have convergent series, the problem is solved. But now we kind of start facing difficulties. We say, okay, who is interested in the weakly coupled link? So we're all interested in the physics of comparison. So what kind of tools we have if convergence is kind of slow or even series divergent? Okay, that's the typical tool. So there are a couple of tools. So one of them I simply illustrate here as a cartoon. So suppose you want to calculate the properties of the tool star. Well, the convergence radius is simply limited by something happening in the complex. But it's in the complex plane of U. It doesn't mean that you have a physical intuition on what it's doing. Because this is for complex interaction. Non-Hermitian Hamiltonian with a node to Y, it's just mathematics of the system. Well, but once you know it, you say, okay, well, is it possible that I rewrite my action in some way? So actually, I don't do the expansion from this point. I do an expansion from something which is closer to the final solution. And the answer is yes, it's possible. Typically, you'll have to change the expansion parameter. You will not expand the decoupling constant. You will expand in the auxiliary parameter side. This is just illustration. We call it shifted action, but you can implement it in infinite number of ways, including cover physiological information. You can manipulate interactions as well. This is just to show how this is factored. You have your original action. You have bilinear part, which you are using to set up the expansion for Feynman diagram. Then you have interactions. If I use this action, I will be expanding in the decoupling constant. But that's the problem I face. My series derivative. So what you do instead, you rewrite your action. Yeah, I'm sorry that some signs don't show up. So you have some totally fake propagator at the bilinear level. It does not even have to be physical. It can violate causality, who cares? So it's just some object which you are using to set up the expansion. But then you have counterterms. Lambda 1, lambda 2, as many as you want, formally not necessarily linear, you can also have some non-linear terms. And you also have psi in front of interactions. And then you see that, well, okay, psi is 0, that's some totally fake quadratic action. That's my starting point for the expansion. But if psi equals 1, I have a requirement. But for psi equals 1, my action is exactly the same as the physical one. So now I'll do the expansion in powers of psi. And it may happen that if I just do this very simple trick, I will end up inside the convergence space. And this was already beautifully used, and you'll see some examples of how this was done by Michel Ferrero. Will give you some examples how you can use this type of tools just to be inside the convergence space when the original series are known. Of course, this is more or less well known in physics as a normalization. You always do. You start with a better starting point. You have, we call them counter terms because they will cancel some of the contributions coming from interactions. And now you can do it. Cancel means we introduce more signs. So we cancel more and more diagonals of high order in such a way that now the series will converge. And the starting point can be anything you like. Can be new field, game of T, Patrick Hawk, GW, some symmetry breaking fields. You keep imagining because this is absolutely kind of generic tool which says you have a lot of arbitrary functions. G is funny here. Lambda 1, lambda n, they're all arbitrary functions. There's only one condition they have to set. Well, now you have other tools. So maybe you use shifted action and it didn't help. You are still outside of convergence radius. Okay, well, I'm doing it in the space of Q, doesn't have much. So you just do this. We all know that, well, when sometimes series diverge, I can always think about, okay, where this divergence is coming from, because if I have enough terms in the power series, I can imagine some other function behind them, which has singularities in the complex way. So just imagine that what's hurting me is a simple pole. If you imagine that the function behind the entire power series is the ratio of two polynomials, which is called Faddeev approximant, you'll figure out that there is probably a pole of first order located somewhere here. You'll never know it exactly because you have a finite number of terms. But it's enough to know it approximately. The moment you know approximately where this is located, you just do conformal map. So instead of expansion in U, you will start expanding in Z. And you will end up inside the convergence radius very nicely. If kind of singularity is that simple, you will easily do it. This is generically, let's say, okay, let's call it conformal map. So if you understand your singularities well enough, do conformal mapping, and in new expansion parameters, you will end up in the convergence. So we have those tools. Well, of course, all of this is known, and the literature is kind of enormous in mathematics. Whether it's kind of Faddeev approximants, which you use to design the conformal map. If you have branch cuts, probably you will use the ratio of Faddeev geometric functions. Maybe you want to use the log Faddeev, Mayer functions. The literature is enormous, but this is all available. So you can always do conformal map once you understand singularity. Let me show you kind of a couple of examples again. Some of this will be in Michel's talk. For example, this is for the Hubble model. If I just don't do anything and do the prime expansion, I find out that, okay, what I want to know is outside of the convergence radius because there's some singularity inside this. You do the shifted action approach and you end up inside the convergence radius, so your convergence will already create. Okay, so we will see some examples, but you can do even better. So this is one of the best examples currently that we have. When convergence radius is simply 0, you can still kind of with proper manipulation of your series, doing conformal Borel, you can actually manipulate series with 0 convergence radius and get the final result, which looks like very nicely convergent with very good error bars. So those are the previous error bars, which were considered super accurate. But now you see that you can do much better for the unitary tensor. The system has no small parameters whatsoever. So this is kind of considered in the field of cold atoms as the most strongly interacting point. Unitary gas when the second length is increased.
And red is the experimental element.
This is MIT experimental, the red one is MIT experiment. This was our previous result before we did the proper conformal barrel. Now with kind of proper conformal barrel, you see that the aerobus will look like this. You look at this and say, yeah, it's still kind of some magic. You do something, you try to get inside the convergence rate. If you didn't get there, you have to use conformal maps. Sometimes they help, but sometimes you have too many singularities and your accuracy very quickly deteriorates, which means divergence is still kind of bothering us in many cases. And now I would like to say that yes, if you have to do the estimation, you didn't do your job right at the action level yet. So you can always manipulate your action in such a way that your cities will always converge, and you don't have to do the estimation level. So that's the last message. So how you do it? Remember that I was talking kind of about the shifted action, and shifted action was only telling us that, okay, if I have the original action, I can manipulate it somehow and add a function which is at the bilinear level. In previous discussion was saying, okay, well, the dependence of interactions on this parametric psi, so far, psi was just in front. It was just the linear power in psi. But if you look at this, you say, okay, there is no reason whatsoever to insist that psi has to be in front of the interaction. Formally, I put interactions inside and make this as a function of psi, such that it's just arbitrary and obeying only a couple of rules. Well, first, the starting point is, of course, arbitrary. You know, I already told you it's designed to be the best starting point. Counter terms are designed to cancel some of the diagonal interactions, but interactions themselves can be also manipulated for the best convergence. Well, because the only restriction actually you have when you write it down, that for psi equal 1, it has to be a physical action. And this term, they have to vanish when psi goes to 0. So there is nothing wrong, for example, to write down these interactions as a power of psi. So this is will be my kind of, I will call it homotopic action. So you have bare part, then you have counter terms, but interaction terms can be also different for different powers of psi. And you start with j equal 1. So for psi equals 0, that's your starting point. When psi equals 1, all of this has to be the same as the interaction. So the effective action, which you are using for expansion now in powers of psi, is totally different, and even interaction terms can be meaningful. Now, how this helps? Because now I can absorb the conformal map inside the action and run the simulation again. So let me kind of show you this kind of trivial. Just imagine I did expansion. So, okay, just simply phrasing that this flexibility has to be used. And typically people are not using this flexibility because there is no guiding principle. So let me now just explain that the guiding principle is available. So what we have, so you can, suppose you do original action and you do expansion in the coupling. The series diverge. So what you do, you say, okay, let's look at the conformal map. But the result of learning the conformal map can be ultimately expressed as follows. You compute your quantity, so you have divergent series. So it's my original kind of writing for the quantity of interest with AJ, GJ outside of convergence radius. But then from conformal map, we simply learn that G can be expressed as some power series in new parametric psi. And if I substitute this into this expression, and we write it as Taylor series in psi, this will converge. So that's the result of the conformal map. We simply write down this type of power series, substitute here, and we get convergent power series in terms of psi. So that's how the conformal map is working. I say, okay, but that's exactly what I will do. I'll take the original action and simply plug in this G to here. So I'll get an action. That's the simplest example I'm just presenting here. So you have the original G0. I didn't even use any shifts here. And then I say, okay, yeah, my interaction now will be split between the orders in a different way with coefficients which I learned from the first calculation. But now you know that if this was convergent, now if I do expansion inside for this action, I will reproduce exactly those series. Which means for this action, the diagrammatic series will be. Now, what's the advantage? If I finish the calculation using the original version, I have some error bars on the coefficients AJ. You do the conformal map, maybe you can remove the first singularity well, but your error bars on other singularities will essentially go out of control. Here, I'm simply learning something, rewrite the action, but now if I start doing the calculation, some of the terms in those series, they cancel between the orders in such a proper way that your variance is much, much smaller. You have convergent series with much, much better error bars. The leading singularity is already removed. And if this still diverges, you will see the next singularity is with good error bars, so you can start removing. So essentially, you can repeat this more or less semi-automatically in the iterative scheme. You'll get the convergent error. So I think, well, this was never used so far. I'm just talking, but there is no algorithm, no calculation, no example kind of to show. But that's doable. I will also skip the discussion that for systems in continuous space, we know how to regularize ultraviolet. It will always have finite convergence radius, and then the entire scheme here goes ahead.
It's possible.
Let me kind of mention it just a little bit, though it's kind of slightly outside of what I was talking before, because what I was discussing before is based on power series, and we have mathematics behind what we're doing. Protect. Well, there are kind of other tools which people use very successfully when they actually have no idea how it works, because you don't have power series, and then I cannot kind of present the mathematics of why it has to work in all cases. This is called optimized perturbation. Well, the idea is kind of more or less in the same spirit, that you have some action, you don't like it, maybe you do some shifts, okay, so you create some other action, but you have shifts and they are parameters. Maybe you have other parameters for interactions as well, so I'm not presenting it here. So you say, which parameters for the shifts I have to use? And what was Stevenson was advocating many, many years ago, also in the context of series, he was saying, okay, well, you have to adjust those parameters order by order. You say those shifts in the action, nothing can depend on them. In the ultimate limit, if the calculation is finished, up to infinite order. But at any finite order, the answer does depend on those arbitrary parameters, number and type. So how do you choose them? They said, okay, well, finish your calculation with all diagrams up to order n. So this is my physical answer up to order n. And simply make sure that those terms, which are arbitrary, are selected in such a way that your answer is maximally independent on the arbitrary choice. You lose Taylor series completely because the calculation you do for order 5 is different from calculation you do for order 6 for all the terms starting from the top. You all optimize parameters once the calculation for the specific order is finished. But sometimes this is just working magic. You can take, say, oscillator, add a harmonic term, like g to x to power 4, or g to infinity, which means x to power 4 terms are much bigger than square. Do perturbation theory, it converges like that. Very good. Sometimes it works magic, but I'm saying, okay, well, I'm less excited about doing this because this is not mathematically rigid as the previous one. The power series. Okay, probably this is all I wanted to say at the level of how diagrammatic Monte Carlo works. Yes, you compute your answer from the series of Feynman diagrams, and if you properly design and kind of manipulate the effective actions in an identical way formally, when the calculation is finished, you can make your diagrammatic expansion to converge all. If you have to resum, you have the tools to go and reshuffle the action in such a way that it will. Okay, let me kind of now just present one physical answer which we did before all of this was known. So this was the calculation of the best one. So this was for interacting topological insulators. Why they are more or less nice application of diagrammatic Monte Carlo? Because often convergence radius is 0 at 0 temperature. But if I have the rock point, it's not a Fermi surface, it's a Fermi point. Your convergence properties are much, much better, and you may have finite convergence radius even at 0 temperature. So in some cases, well, there are a lot of papers which can prove this statement even very good. The moment I have finite convergence radius, you already understand I'm in a much better shape. And sometimes transitions in interacting topological insulators, you can say not the most interesting transitions, but some of them, they're triggered by the band structure. Which means, yes, you have to do some periodic calculation to understand how the band structure changes, but at this level, I don't need a convergence or true phase transition because at the level of manipulating the data structure, sorry, the band structure, I can trigger the transition to the topological phase. So the model we chose was Haldane-Hubbard model. Probably everybody knows it. Just quickly, it's honeycomb lattice. You can have nearest neighbor hopping, and you also have hopping across the diagonal. And this hopping across the diagonal, it has a phase. So essentially, if you go clockwise, it's e to the power minus I pi, but if I go anti-clockwise, it's emission conjugation. This is in plus I pi. Okay, so that's the model, and you also introduce a sublattice breaking, so which means you have different external fields for sublattice A and B, and that's the model which was studied. Okay, so one of the first calculations, this was done in this paper. I don't know if I did here. So the calculation was done for pi or pi over 2, just to see how it works. And this was a little bit kind of nice demonstration of how dangerous some of the approximations can be. So you do mean field, you have this phase diagram. If you do exact diagonalization, the phase diagram changes to this one. To say, okay, roughly similar, maybe some of the parameters change by 50%, but here kind of it looks similar in structure, but here exact diagonalization simply doesn't have enough momentum points probably to see that the line will coalesce, so it will split the transition. But then you say, let's do a little bit better. Instead of mean field, let's do DMT. And suddenly you see that this red point where these topological cases meet suddenly flies out of the screen. So it's some way. So instead of 2, I think the proper value goes roughly to 2. So here at this point, you start kind of be a little bit nervous because depending on which scheme I use, I have a totally different phase diagram, especially for the triple point. It can be here on the screen or even outside of the screen. So, but as I already explained, okay, well, diagrammatically, we can go do much better. So it's not only the field, we can do the field as our starting point, but then we can do diagrams to higher order and try to get convergence. So that's more or less kind of the demonstration that for this type of problem, diagrammatic Monte Carlo is very well suited. So that's the correct phase diagram. So essentially, yes, the triple point does not fly out of the room. It simply changes from the near field maybe by 57%. But otherwise, it's pretty close in the location of all lines, except, okay, this is one line, it's not split to what the exact diagonalization was. Except this is now limit. And I think we are pretty confident in every single point. Arrow bars are shown, but they're smaller than the symbol size. At that time, we didn't know how to handle this part of the phase diagram. So because this is not insulated, and for everybody working on the Hubbard model, we know this is extremely tough. Now this barrier is broken. Now I understand how to do convergent simulations even in the not insulated case. So, but this is kind of pretty fresh, no papers published yet. So probably this part will be also possible, and then the entire phase diagram can come. This was not done at the time when we configured this part of the paper. Yeah, so probably I'll stop here. That's very simple conclusion that yes, diagrammatically you can solve the problem. But in the strongly correlated regime, probably you have to work pretty hard to understand how to design and optimize your effective action. But now I think we're switching from art to semi-engineering. So there are some semi-automatic procedures which can be applied to make sure that your expansion converges always. Thank you.
And what can be done to simulate disorder?
No, you can simulate disorder, but I cannot guarantee you will succeed. And my experience so far was bad. No, I cannot answer. I don't know how to solve the problem, so I cannot give you an advice.
Are there examples where they're successful diagnostic calculations?
With controlled error bars?
Yes.
No. Without control on error bars, yes, tons of it. But if you want to say that I bet my annual salary that my answer is exactly this with error bars, good accuracy, I don't know.
What about only single particle disorder? That if you have a coupling constant that is uniform in space, but you have.
Well, there are very simple theorems in disorderly systems which are called rare regions. Suppose you very trivial example. Say, yeah, single particle disorder. But single particle disorder, you think it's random, but rare region can be a regular potential. It can be a more lattice, okay, which period, any of them. So there can be a region with this period, there can be a region with twice as small period, there can be a region with yet another period. They happen in the simulation. Do you believe that I can have one solution when I can solve all Moira potentials at once? No. Let's do them one by one. Probably that's doable. But all of them at once in one simulation, because sooner or later your accuracy will hit that you have to reproduce. I think it's just not believable. So unfortunately, this kind of rare region argument, they're always with us, which means random disorder with unlimited support can represent any external potential you can imagine. And that's the problem.
So, yeah, how dependent is this approach in practical applications on using short-range interaction models like the ones
You pay zero price between short range and long range. That's cost range. Depends, of course, on the representation. Some people write down codes in momentum representation, then it costs you nothing. If you write it down in real space, Hubbard model has a little bit special properties. It's not just short range. It's just local and spin up and spin down couple only. But otherwise, there is no difference whatsoever. Just long range or short range, you don't care. They're Feynman diagrams, you know. You just draw the diagram. You don't care much whether it's short range or long range.
If you do the series expansion, are your results in the end going to be analytical? Analytical, is that like the problem with the technical picture?
The answer is not analytical. It's power series up to largest possible order. If you approach the true physical transition, you'll definitely face a problem. This is not removal because it's true physics. So then probably the best option we have at the moment is just to introduce symmetry breaking field and simply try to extrapolate in the symmetry breaking field to zero. You introduce it explicitly, finish the calculation, and extrapolate the answer. Yes, you can study phase transitions and determine critical points with accuracy on % level.
Last question.
Do you have problems when you are close to critical points? Some critical slowing down?
No, there is no critical slowing down because there is no system size. Critical slowing down about finite size. There is no finite size. We definitely will face convergence properties. And the rest will be how well you can manipulate them and understand them. But definitely, if it's a physical transition and your point which you're trying to simulate is right next to the singularity, you'll start losing accuracy. Probably you can locate the transition point with 1% accuracy, but then your accuracy will be much, much higher. But inside the phase, it's much easier.
Probably move on to this is the end of the morning session.
Yeah, do we have a general discussion on that?
There wasn't one slotted in.
All right. Well, let's thank all the speakers then.